Hello, my name is Anastasia Shuba, and I'll be presenting NoMoATS towards automatic detection of mobile tracking. And this is joint work with my former advisor, Athena Morkopoulou, from the University of California, Irvine, which is where I was when this work was conducted. Currently, I am at Broadcom. However, this presentation does not represent Broadcom's views. So all of us here know that mobile devices have access to a wealth of sensitive data. For instance, our entire contact list, various sensor information from GPS, microphone, and accelerometer, and various device identifiers. For the rest of the talk, I will refer to this data as PII, or Personally Identifiable Information. Now, we know that applications often have legitimate reasons to collect PII. For example, Google Maps requires our location to function, so our phone will often send our latitude and longitude coordinates to Google Maps. In this case, the access is legitimate because we have given Google Maps permission to collect our data. However, permissions are not enough. Let's take another app, for example, say Pokemon Go. It also supposedly has legitimate reasons to collect our location data, and it also integrates with several third-party libraries, for example, Unity 3D for graphics rendering, Facebook for providing like and share buttons, and advertising libraries. And once you've given location permissions to Pokemon Go, all the libraries contained within it have the same access. Second reason permissions are not enough is that trackers have evolved from collecting explicit PII to collecting seemingly benign information, which we refer to in literature as a fingerprint. Here's one example here that is collecting the width and height of the device, the battery status, whether it's rooted or not. And collectively, this information can be used to build a profile of you and then track you across apps and libraries. All of this is driven by the multi-billion-dollar advertising industry. So applications will also often send out ad requests to the ad networks, and the ad networks will then respond with an ad that will pop up on your screen. For the rest of the slides, I will refer to advertising and tracking as A&T. So what can be done about these things? There have been several approaches in prior art. Here I will focus on one that is most closely related to ours, which is a network monitoring approach. And the idea here is that we can place a VPN server on the network path, inspect the traffic, and then block it as we see fit. This was done in Metal and in our own prior work called Ant Monitor. Future works have explored the opportunity to remove this VPN server and do the VPN interception on the device alone. For instance, Lumen, Privacy Guard, and a later version of Ant Monitor. Once this network interception is in place, we can block different manifestations of A&T. For example, in our own prior work, Ant Monitor, we focused on blocking PII. So we essentially maintained a filter list of PII, and whenever a packet contained one of the strings in our filter list, we blocked that packet. Unfortunately, our approach was unable to deal with ad requests and fingerprints being sent to trackers. Another related work here is Recon, where they moved from a filter list approach to a machine learning approach. And they used a classifier to detect whether or not there was PII in a particular packet. Since we're now introducing machine learning, we now also have to worry about labeling our data. In the case of Recon, this was automated because they could use a test device for which PII are known and then build classifiers off of that data. However, again, Recon was unable to block ad requests and fingerprints. So another approach here is one that originates from browser tools that are mostly used for ad blocking, and one of such tools is AdGuard. So AdGuard maintains a much more complex filter list that attempts to block all these manifestations of advertising and tracking. The only problem with AdGuard is that it requires a lot of manual labor, as I will show you in the following video. Let's say we want to block this advertisement here in LA Times, and we see there's a page ad request. So we can use the AdBlock Plus extension here to block that request in the next reload. Unfortunately, when we do that, we still see the ad, and we still see some page ad requests. So perhaps our rule was too specific. We can try and make it more generic here. And then reload the web page again. Unfortunately, we still see the ad, although more of the page ad requests were blocked. So now we have to go through hundreds of these requests to find one more candidate to block. Okay, this one, secure pub ads, looks pretty good. Let's try to block that. Reload again. And this time the advertisement is not there. So in another prior work of ours, NoMoATS, which was also presented at PETS 2 years ago, we attempted to improve on the AdGuard approach and proposed a machine learning based approach that would replace filter list rules. Since at the time there was no mobile specific rule set, we followed an approach where we used an existing browser specific filter list and supplemented it with our own labels. So I got a hands-on experience with creating these rules, and I found out how tedious this process was. At the same time, because I relied on a visual cue of seeing an ad there to figure out when I need to go back to the network traffic and create a new rule for ad blocking, I was unable to do this for tracking. So we were only able to block ads in NoMoATS. Some of the feedback that I got at PETS was asking me if I can further automate NoMoATS and if I could extend it to block trackers as well. And this is exactly what we attempt to do in NoMoATS. We follow a machine learning based approach that can block all three manifestations of ANT, and at the same time it requires minimal labeling efforts. So our vision for NoMoATS was as follows. We wanted to have some black box that, given network traffic, would spit out that same network traffic with labels. This is the main contribution of NoMoATS. It is the first system for automatically labeling packets as being destined to advertising and tracking services. The labels can then be used to train NoMoATS-like machine learning classifiers, as I show you here next. So on the server side, we have NoMoATS collecting data, and then that data can be fed into training machine learning classifiers. The classifiers can then be pushed to the Android device, where we also have a VPN interception service, such as AntMonitor. This service will then feed the traffic data to the classifiers, and the classifiers will provide back a decision. Another thing provided by VPN services such as AntMonitor is the ability to map packets to applications, so we can potentially build specialized classifiers that are tailored to a particular app. So next I will describe our NoMoATS system. This is where our main contribution is. And then later I will describe our machine learning approach. So first, how do we build NoMoATS? Let me share with you some insights we had prior to building this. Our primary interests here are third-party advertising and tracking libraries. And one thing to note is that application code is separated into labeled packages. For instance, here I am showing the Zedge app, which is some wallpaper app, and we see the package belonging to Zedge itself, as well as several packages belonging to third-party libraries. And the second thing to note is that stack traces indicate package names as well. So here I show an SSL handshake being initiated by the mopap library. Here's one more stack trace where we don't see any third-party library, we only see the Zedge app itself, which means it alone is responsible for generating this SSL handshake. Now, if you could just find a way to collect stack traces at the network API access point, we could potentially build our automatic labeling tool. Before I go into the details, let me provide you some background on Android networking APIs. And I'm focusing on Android because we have built our tool for Android, but the same methods can be used in iOS systems as well. So if I'm an Android app developer and I want to access the internet, I have several options available to me. I can use the Software Development Kit, or SDK, to access various APIs, for instance, socket APIs, which then gets translated into the native development kit socket API calls. And these get further down to the Android operating system's standard C library send-to call. Another way I can access the network is I can load my own native library, which directly accesses the NDK's socket APIs, but these again end up going to the send-to call of the standard C library. If I want to send encrypted traffic, I can use SSL APIs provided by the SDK, which then go on to the OpenSSL implementation within the Android OS, calls such as SSL write. There's no native version of this. So if you could find a way to hook into these API calls and collect stack traces there, we get one step closer to our goal. In our work, we used Frida, which is a system usually used for penetration testing, but we used it to hook into our calls. Now, this requires a rooted device, but that's okay for us because this part is running on the server offline. We placed several hooks, one in the send-to call to intercept plain text traffic, and one in the SSL write call to intercept encrypted traffic. And with this, we were able to collect all the network traffic, but we ran into one problem. So there's this component in Android called WebView, and all requests coming from WebView first go through the WebView system app before ending up in the send-to call. So we have no way to differentiate where this originated from, the app or a library. To deal with this, we placed an additional hook for WebView traffic inside the WebView system app. And with this, we had our full capturing tool. To take the traffic from the Android device, we use the Frida client that talks to the Frida agent on the device through USB. And from there, we're able to collect network traffic data in any format that we want, for instance, PCAPNG. One last thing that we need here is a way to automatically explore apps. For this, we used prior art, a tool called DroidBot specifically. And DroidBot works by exploring the UI elements of apps in a breadth-first search or depth-first search manner. Here's an example output of PCAPNG trace captured by our tool. Here I am highlighting what is obviously an add request. And inside the packet comments, we see that this SSL write call was initiated by the mopub library. So now going back to this question that we had, how do we label traffic automatically? Well, if this traffic is also prepended with stack traces, all we need to do is match the stack traces with a list of known advertising and tracking libraries. And such a list will always be available because developers also need to know what libraries to use. And in the ecosystem, there's only 100 or so of these libraries. And once we've labeled them, we're done, as opposed to continuing to label HTTP requests for various apps or pages like we saw earlier in the video. So this concludes the system overview. Let me next describe our machine learning approach. So using our system, we collected a new dataset of 307 apps, taking the top 10 free apps from the 35 Google Play Store categories. And automating these apps, we collected 37,000 packets, 13,000 of which were sent by advertising and tracking libraries. Using this data, we trained several classifiers. First, we trained what we refer to as a general classifier, meaning we took our entire dataset and trained one decision tree on that dataset. And we evaluated using various features on this dataset, starting by using the hostname alone. With this feature alone, we were able to achieve an F1 score of 90%. And the training time here was fast because it's just one feature. Next, we evaluated other features. Here, I will only focus on our full feature set, which is the full URL and all the HTTP headers. Please refer to the paper for more details. So using more features increased our F1 score to over 95%. However, the training time went up to close to 6 hours. And the resultant tree node size was 371 nodes. To see if we can improve on this, we also explored training what we refer to as a per app classifier. So taking a particular app's data alone and training a specialized decision tree for that app. Here, using the hostname alone was already outperforming the general classifier and achieving an F1 score of 93%. Again, training time is fast and tree node size is small on average. However, when using the full feature set on the per app classifier, we noticed that it does slightly worse than the general one, but still achieves a high enough F-score of 93%. And on top of that, its training time is much faster. It's only dozens of milliseconds compared to hours. And the resultant tree size is small and intuitive. So here's an example of one such tree. We see that whenever there is an app ID parameter in the URL, we'll label the packet as advertising and tracking, or when there's Crashlytics, again, we label it as advertising and tracking. In terms of prediction time, Both classifiers perform well in the orders of milliseconds, so both can be used on top of a VPN interception service and predict packets in real time. However, we recommend the per-app classifier since it's much more intuitive to look at and faster to train and retrain when apps update. To evaluate our approaches, both the NoMoATS labels and our classifiers, we took our dataset and fed them through several filter lists. Specifically, we used EasyList, which is the most common list used for ad blocking in browsers, and EasyPrivacy, which is used to supplement EasyList and block trackers as well. We also used a mobile-specific list, which has an interesting name. It's called Mother of All Ad Blocking, which I will refer to as NoMoAB. Using these lists, we labeled our data and then compared these labels with our own NoMoATS labels. So out of the 37,000 requests that we collected, both approaches, meaning the lists and NoMoATS, labeled 16,000 samples as negative. In terms of positive labels, here's a Venn diagram of the approaches where I've merged EasyList and EasyPrivacy together. And here we can see that EasyLists are the least aggressive of the three approaches, labeling only 7,000 samples as positive. NoMoATS is somewhere in the middle, labeling 13,000 samples as positive. And NoMoAB is the most aggressive of the three, labeling 17,000 samples as positive. However, this does not mean that NoMoAB is the best. Looking at these 5,000 samples where NoMoAB disagreed with the other approaches, we found several false positives. For example, the OkCupid app sending something to OkCupid, or the Amazon app sending something to Amazon. Exploring other disagreements between NoMoATS and the labels where EasyList and NoMoAB agreed, but NoMoATS disagreed, we found that the main reason behind NoMoATS missing these samples was that these were sent by multi-purpose libraries. For example, Facebook is a multi-purpose library that is often used to provide login functionality or other needed functionality like buttons and share buttons, but it can be also used to track users. And currently we have no way to differentiate which purpose is served in a particular instance, and this is something we hope to address in future work. Another thing to note in this Venn diagram is that there's a large overlap of agreement between NoMoATS and the filter lists of about 10,000 samples. And this indicates that NoMoATS can find the same samples as the lists without requiring that intensive manual labor. Finally, NoMoATS also finds new samples, as the one I show here, about 3,000 of them. And a lot of these samples are actually going to mobile-specific advertising and tracking services such as Startup, AppLovin, and Tapjoy. So this also indicates that NoMoATS can be used to supplement existing filter lists. Using this evaluation approach, we also evaluated our decision tree classifier. Here I will mainly talk about the general one, but we also evaluated the per app one in the paper. So we compared the labels provided by the decision tree to the other approaches. Here's a simplified Venn diagram where I show the classifier NoMoATS and the lists combined. As expected, the classifier and NoMoATS are largely in agreement with each other because that's what the classifier has been trained on. The classifier is slightly more aggressive, however. It labels close to 14,000 samples as positive. And some of these supposed false positives that the classifier finds are actually in agreement with the filter lists, so it means it's able to overcome the false negatives in the NoMoATS labeling system. There are of course also some false negatives, and most of these we hope to fix by better data balancing and also improvements within NoMoATS itself. To conclude, I presented NoMoATS, which is a system for automatically labeling which packets are sent by A&T libraries. The data collected with NoMoATS can be used to train classifiers, and evaluation with popular filter lists shows that both NoMoATS and the classifiers can be used to either supplement or replace existing filter lists. In terms of future directions, we hope to address some of our current limitations. For example, how to deal with multi-purpose libraries, and how to detect when an application breaks when we block something. We are also looking to extending NoMoATS to other platforms. Our code and dataset is available on our website. Feel free to explore it and send us questions if you have any. Thank you.